3, 2, 1.
Hello, I'm James O'Loughlin. Welcome to Innovating for the Earth, the story of the development and use of new technology developed by Calix. It's technology that helps industry address environmental and sustainability challenges like crop protection, aquaculture, wastewater treatment and carbon reduction. We've previously looked at how the Calix technology was developed and how it works. Today, how is the Calix technology being used in the cement industry to capture carbon dioxide and reduce emissions? My guest is Calix project engineer Simon Thomsen. Now, Simon worked for Calix while he studied mechanical engineering at the University of New South Wales in Sydney. Back then, Calix was still developing the technology, and after Simon graduated in 2011, he joined Calix full-time, and he's worked in many roles. In 2017, he moved to Europe to work on the LEILAC project, which you'll hear more about in a moment. Welcome, Simon.
Thanks, James. Very nice to be here and talking to you.
Now, we're going to talk about how the Calix technology is making a difference to the cement industry. Let's kind of look at the problem, if you like, that it solves. Firstly, how much carbon dioxide does cement generate every year in a way that I'll understand?
It's actually hard to describe the numbers because they're so big. I mean, the human race emits roughly 50 billion tons per annum of CO2. So cement of that number is about 8%. So it's almost 5 billion tons per annum. It's a huge number. To compare it to something else, which is, I suppose, something that we deal with more on a day-to-day basis, vehicular transport, road transport emits about 12%. So although cement and lime emit less than road transport, as we're able to start decarbonising the road transport industry, the proportion of CO2 emissions coming from cement and lime will increase. And the problem that they have at the moment is that there aren't solutions readily available on the market for decarbonising the cement and lime industry. Whereas for road transport, it's still on the horizon a little bit, but there are solutions such as electrification, which are almost ready right now. Yeah.
And in the coal industry, it's gradually, being replaced by renewables, a gradual transition. But cement and cement in particular, it's hard to see. Well, there isn't. Is there a readily available substitute on the near horizon?
No, and that's the tough thing. It's also very separated from the everyday person. Like I don't look at a building and think, wow, the CO2 emissions from that building are huge. Like it's just this immobile object which it looks completely harmless. But for every ton of cement that you use, you're emitting roughly a ton of CO2 into the atmosphere, and it's something which 60% of that emission is completely unavoidable. So it's a part of the chemical process of producing cement. And so even if you were to produce that cement using wind turbines and solar, you'd still be emitting that CO2. And that's really where there needs to be a solution developed.
So I know how my car creates carbon dioxide. It burns petrol and out it puffs from the exhaust pipe. How does cement production generate carbon dioxide?
Well, a part of the cement production process is the calcination of limestone. So to break down what that actually means, that's taking a mineral, a rock, heating it up to a very high temperature, and in doing so, it actually causes the CO2 that's attached to the rock chemically to become detached from the rock. And that the product from that process, lime, is one of the chemical components of cement, or required in the cement production process. That then goes on into a rotary kiln, which is a big long kiln which has a big flame at one end to turn that into the clinker, which forms the cement. But the calcination of limestone is inherently a part of producing the chemical precursor for the cement clinker. And it's not something where you can go and find a deposit of lime in the ground and use that instead. It doesn't exist. So you need to find limestone, you need to process it thermally to remove the CO2, and the product from that process is then used in the production of cement. So there are no alternatives, basically, if you want to use cement.
Right. So, and did you say that accounted for about 60% of the carbon dioxide produced? So what about the other 40%?
The other 40% comes from the heating process. And at the moment, the cement industry it will use RDF, which is a waste, refuse-derived fuel. So that might be, what gets picked up by the garbage truck that comes outside your house. That might end up in a cement kiln somewhere. Or it could come from coal, or it could come from natural gas. And they're starting to develop other solutions as well. But again, they're a bit on the horizon. So there might be the possibility to produce cement using a plasma or some electric heating source, but it's much more difficult, and it's something which is still being developed at this point in time, just like our technology.
So the solution to coal emissions is using more renewable energy. The solution to motor vehicle emissions is a transition to electric cars. But I think what you're saying is there's nothing similar that's there or about to be there with the cement industry.
Yeah, that's exactly right. And as I was saying, the heating portion of it is just one part of the problem. So taking the car example, if you were to replace the the motor in a car with an electric motor, you are solving the problem as long as the electricity comes from a renewable source. It's not the same in cement where you replace you can't just replace the heating source and wash your hands. There's still 60% of the current emissions come from the process.
So before we get to how the Calyx technology might help solve this problem, are there other solutions that people have been trying?
Yeah, there are lots of solutions that people are looking at. I mean, the cement and lime industries are becoming a bigger focus, I would say, with respect to decarbonisation, because the other industries developing solutions which are coming much closer to market. These two industries, I guess they're a little bit behind the others. They still need to develop solutions. And so we're one of a number of technologies that may be able to serve that industry. And, speaking as a person who lives on planet Earth, who wants to see planet Earth not kill all the people on it, I don't really mind which solutions are successful. Obviously, working at Calix, I would love for our LEILAC technology to be successful, but I would be equally happy if all of the other ones were successful. And frankly speaking, cement and lime produces so much CO2 per year that we kind of need everything to work to solve that problem.
So let's talk about the Calyx solution or attempted solution. What happens?
Okay, so basically, as I said, at the moment, the energy to heat the calcination process comes from something burning. So coal or waste or natural gas. That process produces CO2, but it also produces a number of other gases. And the problem that exists in an existing cement plant is that combustion process happens with the mineral, with the limestone that you're trying to calcine. That means that all of the CO2 that's emitted from the calcination process, from heating the mineral, is then mixed with all of these other gases like nitrogen. And the problem with that is that if you want to take the CO2 and use it or sequester it, you then have to separate it from all of those other gases, which is extremely difficult and expensive. The solution which Calix has is to basically put a wall between the heating process and the calcination process. So all of the CO2 that's emitted, the 60% of that CO2 that's emitted through the calcination process, is emitted in a closed system, which means that the CO2 is pure. So they can take that CO2 and without any other process, they can utilize it or sequester it, which is extremely useful. And the fact that our technology is able to be very cheap, both to operate the process and to actually build the plants in the first place, that makes it very advantageous.
So this is big technology to develop. Did you have partners and assistants?
Yeah, very much. And really, LEILAC is a group of companies which are working together towards this goal, and it includes cement companies such as Heidelberg Cement. It includes Cemex, Simpor in Portugal. It includes limestone companies such as Lamaste. But we also have research partners who are helping us. CERT, who are in Greece, are involved. We also have partners who are there for aiding us in communicating what we're doing with the public. We have partners who are involved for the purpose of modeling the improvement that comes from our technology, because it's kind of not as simple as just saying, well, we can capture 60% of that CO2, that's 60% tick. You need to look at the whole life cycle of the technology, all of the equipment that you need to use to make it work, and then you need to say, once we include all of that compared to everything that's included in the current technology, are we still beneficial? And so that's a huge task, actually, to look into that detail, to model it, and then be able to communicate it. Yeah.
It sounds extremely huge. At what point are you now? How far have you got?
Yeah, well, at the moment where we are is we've been able to demonstrate the fundamentals of the technology in the LEILAC 1 project. And LEILAC 1 as a project just finished its 5.5-year lifespan. The purpose of that project was really to take our technology and apply it into the cement industry at a relatively small scale. So we put in a single one of our reactors, which processed about 5% of the total CO2 emissions from a plant in Belgium. The purpose of that was not to replace the entire existing process. It was just to demonstrate and develop the technology in situ, operating on the actual cement meal and using the actual fuels. That was an important first step. Where we are now is we're trying to take everything that we've developed and we're trying to apply that at a scale which is large enough that it is applicable on any cement plant. So it's still 20-25% of the total scale of a typical cement plant in LEILAC 2. However, at the scale that it will be, we will have solved all of the challenges that come with scaling up to apply it to any plant.
Wow. So going back to LEILAC 1, building the original plant, given one had never been built before, that must have thrown up many challenges.
Yeah, it was an extraordinary challenge to build LEILAC 1. I'm glad to say that we were able to do it successfully on time and on budget, but it was a huge challenge and it required a lot of work from everyone involved at all levels of the project.
Did things go largely to plan, or alternatively, did you have to change the plan a lot?
Yeah, that's a really good question. And as anyone who's involved in projects would know, you've got three things that you need to focus on: time, the budget, and your scope. And we did need to make decisions around the scope as an example in order to keep the budget and the schedule together. An example of this was that we were looking at some things that were not entirely required to demonstrate the technology, but would have been improvements from an efficiency standpoint or things like this, such as we were going to preheat the cement meal before it went into the reactor. We made a decision to instead focus only on the reactor itself in order to keep the budget in shape. So that was an example of a project management decision, which was a difficult one, but it was ultimately the right one because, the technology can't be successful if the project isn't successful. And we were able to make the project successful. And so we've been able to demonstrate the technology in Belgium, and that's allowed us to move on to LEILAC Stage 2. So
was it a little bit like I write stories and I have a kind of vague idea where it's going, but I don't know exactly where it's going. But then when I get a bit further into it, I can kind of see what's going to happen next, and then when I get to that bit I can see what's going to happen after that. Like did you have a big plan, and then as you got further into it you could see more specifically what had to happen next, what you could keep as planned, what you had to change?
I think that's a great analogy, actually, because, again, this is a brand new technology, so it comes with a huge amount of research and development. So when we started the project, we couldn't say exactly what everything would look like because there was a big research and development project, sub-project which had to happen in parallel to develop the components that then needed to be engineered and put in. So at the start of the project, it was impossible to say it will cost exactly this much, it will take this long to build, or it will look exactly like this. We had to start the project, start doing the work in order to unveil those pieces of information and then complete the project. And it was for that reason that everyone had to be very flexible, which it's quite difficult from an engineering standpoint because it takes a lot of work to build anything. And every time a change comes into the plan, it requires a lot of other things to change as well. So, I think that's a good analogy. Yeah, a little bit on the run.
And flexibility, flexibility is exciting, but it also creates a lot of anxiety in people, doesn't it? Did you have to manage that and your own?
Yeah. I think that again, the closer you get to the people who are building things, the engineers, and then the construction people, the more anxiety that causes. But at the end of the day, you kind of just need to make sure that you communicate the reason for the changes as they're coming up, because there's always a good reason that something has to be done. But someone who is turning a bolt on a piece of steel or equipment isn't immediately isn't seeing that as obviously as the engineers are or the people in the R&D team. So yeah,
that's a great point actually, because it's really easy for people to be told things and think, oh, management, they're just changing their minds, they're hopeless. But as you say, if you explain exactly why, then you're more likely to get a unified team.
Yeah, it's super important. It's really important, and I think it's a big mistake that can happen in a project such as this is not communicating accurately or completely the reason that things are the way that they are, because people get disenfranchised or lose interest or things like that. And at the end of the day, you can talk about the technology or the project or the companies that are involved, but it's the people in those companies who are actually making those things real. And if they lose their passion or if they lose their interest, no matter how big or how much money is thrown at something, it's just not going to happen. So yeah, it's been really important.
Well, you said it's important in projects like these, but it's important in any organisation. I don't know if you've had the experience of, ringing up your phone company or talking to someone in a hotel, and all of a sudden, they start complaining about how hopeless management is. And you think, wow, this is a troubled organisation.
Yeah. It's you're exactly right. It's the same problems that they're facing that we're facing. Yeah.
So, Simon, LEILAC 2, where are you at the moment?
Well, LEILAC 2, so as I said, we've kind of been successful in demonstrating the technology, but there do remain challenges in the technology itself which need to be resolved in order to make it as large as it needs to be commercial. It's actually not as easy as just taking, a design for something that works, sticking it on a printer and saying print it 200% and it will be 200% bigger, Scaling up technology is very difficult and complicated, and it's for that reason that we needed this LEILAC 2 project to take all of our learnings from LEILAC 1, find the challenge with scaling it up, and solve those challenges. And so my responsibility in the LEILAC 2 project is actually I'm managing the work package which is responsible for the R&D, but because of my background as an engineer, I see it sort of from both the R&D and the engineering perspective, and I'm able to take the engineering challenges or the things that need to be known in order to build a plant and develop an R&D program to resolve those challenges. And so that's sort of where we are at the moment. We've gotten through our what we call the pre-feed, basically a feasibility study for the project. We've uncovered all of those challenges that we need to resolve. We've resolved most of them. There do remain a few which we need to complete, but we have a program to complete those, to close out those challenges by November of this year, and we're well advanced in our work in resolving those challenges. So
this must be costing an enormous amount of money. Are you still in the kind of investment stage? Hoping and being confident that you'll get it right and suddenly we'll have a very scalable, saleable technology.
Yeah, well, I suppose that's where, yes, there's been investment from the industry. Our partners, our industrial partners who want to have a technology available to them are investing heavily in the project. We also have a huge amount of money coming in from the European Commission through their Horizons 2020 scheme in the form of grant funding. And I think that that's really instrumental in making something like this possible because, as you say, developing technology is hugely expensive and resource intensive. And as much as it would be wonderful if all of the companies on the planet could just invest in resolving these future challenges, at the end of the day, it's a global, worldwide problem for everyone, and governments getting involved. It really does help. It does help make things happen. Yeah.
Yeah. And there's a demonstrator. Now, what is that, and what does that mean, and where are you at with that?
Yeah, so I suppose there are a few different terms for what each different thing will be. We have what we call a pilot in Belgium. That's the very small scale one. Well, I say small scale, it's 5% of a cement plant, but it's still a 60-meter tall tower. So small on a certain scale. That's our pilot, and that's the one which was just demonstrating the technology itself. The term demonstrator, what that means is basically it's demonstrating the technology that will be applied onto cement plants. So again, it won't be the full scale, but it'll be at a scale which is completely relevant and is able to then be, scaled up the little bit up and down that it needs to be applied anywhere. And so that's
it serves the same function as those little bottles of perfume. That you can have a little whiff
the trial
of
bottle, yeah.
Just see if you like it. It's just a little bit bigger and more sophisticated.
Yeah, exactly. And so LEILAC 1 is the little taster bottle that you get in the airport, and then LEILAC 2 is the big sample perfume bottle, and then we'll soon enough have the full perfume for anyone that needs it.
So just so I've got this right, you were talking initially that 60% of the carbon dioxide that is produced in the creation of cement is inevitable. So we're talking about this being a solution to that 60%. Is that correct?
Yeah, that's a really good point. Yeah, because there does remain, even with our technology, the need to heat the process. But the benefit, I suppose, of what we're doing is that because we're separating the process from the heating source with a wall, basically, the heat is able to come from any source. And so we already, or when I say we, Calix already has plants operating which are running on electricity, which can come from a renewable source. So that 40% which we're not dealing with, which our technology is not focused on, is still able to be resolved using conventional technologies, low carbon electricity, or any other source of low carbon fuel. So it's something where we can kind of collaborate a bit with other technologies as well, because there are other ways to capture emissions from combustion sources, and we just make it a lot easier by already taking away that 60%, the majority of the CO2 that's emitted. Yeah.
So that 40%, the remaining 40% of carbon dioxide, that's not core business for you. But on the other hand, that is something you are interested in collaborating with others to try and create solutions for.
Well, I suppose I would probably articulate it as it might not be necessarily core business for LEILAC. LEILAC is still using conventional combustion, but it is core business for Calix. We are developing, or we have developed, actually, I should say, electric calciners which are in operation. We have one in operation in Australia and one which is coming online in Seville in Spain. And if we were to just apply those technologies to LEILAC, we would basically be addressing 100% of the CO2 emissions from the cement and lime industries. So I think that's our solution.
So that could be LEILAC 3. Could that be LEILAC?
Yeah, that could be LEILAC 3. Absolutely. Yeah, and it's really up to
with the initial. The initial 60% of carbon dioxide that LEILAC 1 and 2 are specifically focusing on, are there, I mean, you very generously said earlier that the more technologies in this space together, because we all want to solve this problem, because it threatens the world. It
affects all of us, yeah.
Yeah, so I don't want to use the word rivals, because it's not like you're competing to sell the most chocolate bars. But are there other technologies that are trying to do the same thing? And if so, do you see yourself in some way being in competition with them?
Yes and no, I suppose. I mean, again, from my perspective, our technology directly addresses a portion of the CO2 emissions without any further processing. That doesn't mean that another technology couldn't be applied to that 40%. So there are solutions the solutions such as amine scrubbing, which is a technology where they run the CO2 emissions with the nitrogen and everything through these chemical scrubbers, which extract just the CO2, and then you're able to run the amine, which has captured the CO2, through another process to take the CO2 back out. That sort of technology does already exist and is they're developing it for the cement and lime industries, just like we are. There are other technologies such as oxy-fuel, where they burn the fuels that they already burn, but in an oxygen stream to get rid of all of the other nasties that are in the combustion process. Those technologies can exist alongside our technology. So they could be applied to a cement plant which is running off the LEILAC technology. And in fact, it might be attractive depending on the scenario at a certain location. So yeah, I guess it depends on how brutal you are, whether you consider them to be competitors or, again, really from my perspective, we can collaborate or we can apply all of these things, and we'll have to, frankly, apply everything that we can to resolve this problem. It's just too big to solve one way. Yeah.
Yeah. And you're optimistic, and you've now been through LEILAC 1 and into LEILAC 2, and so it's not a kind of Pollyanna-ish optimism. It's a well-founded, rational optimism about the ability of your technology to make a big difference. And then presumably, if you do prove it, then just the right levers have to be pushed, perhaps at a governmental way or somewhere to incentivize companies, to want to buy it and use it.
Yeah. And look, I know that we've got a colleague of mine, Daniel Rennie, who is our general manager of cement decarbonisation. He'll have a lot to say on this particular topic because it's very relevant to him. But yes, we will need incentives to, I suppose, drive this change, because it doesn't cost anyone anything to emit CO2. So as long as it costs €1 or $1 more to capture that CO2, it's already not economically attractive. So there does need to be some mechanism to incentivize people to do that. Just maybe going back to your point about the optimism that's required, I think that it's really easy to say in hindsight it was reasonable to be optimistic, but I always love to think back to the start of these projects when you don't have something successful, you don't have the technology already successful, and you have to build and maintain the optimism within yourself and within the team and within all of your potential partners to get everyone on board and working on the same page. And yeah, I think that there is a point in time when your optimism needs to be not unfounded, but you do need to really build it. You do need to build optimism before you have something concrete to point at. Yeah, to justify.
That can be tough, can't it?
Yeah.
There can be times when you're lying in bed at night and just thinking, is all this effort of all these people, is it going to end in nothing? I mean, it can be quite terrifying, can't it?
Oh yeah, but it's a fundamental part of these research and development projects. You have to go into them knowing that it is something that's never been done before. There are aspects of it which are unknown, and so you might come across something which tells you that it is not possible. And you still have to maintain the optimism and maintain the drive to answer that question before you can go any further. So, yeah.
Well, that creates the excitement too, the adventure.
Absolutely, yeah. I love that aspect of these projects, actually, because so many times you run into something which is... a lot of people would just look at it and say, oh, that's too hard, or it's not possible, and you just have to find a way. You just have to. Yeah.
And you have, and well done. And look, before we end, I want to ask you about this. You have built a Formula V racing car of your own design, and a couple of years ago you raced it and won a Division 2 championship. Now, can you tell us a bit more about that?
Yeah. Well, I suppose it was a bit the same thing as what LEILAC has been in a very small form. It was an idea I had. I looked at this category which I was racing in at the time, and I could see a few things where I said to myself, well, if I were to build my own car, I would do it this way and this way. And I actually
what do these cars look like, Formula V?
Oh, it's like a little baby Formula One car, but without the wings.
Yeah,
And yeah, so I kind of just... There was no point in time where I decided I was building a car. It kind of was just, I made decisions that ended up forming a car. Like, I think I could buy this engine, or I could buy this bit, and then I could figure out how to do this. And, before too long, you end up most of the way down building a car, and you're like, okay, actually, I'm building a racing car. And then I raced it. I didn't actually win races, but there were two divisions within this competition, and because my car was new and I was new into the competition.
Were the two divisions people who built their own car and everyone else?
No, it was people who, as long as you finished above a certain position in a championship, you would be in Division 1. And because I was new, I wasn't in that position. So I suppose it was a little bit easier for me, but at the same time, it's a bit of a tick against this little project of mine. Yeah.
Definitely. Any crashes?
No, thankfully. No,
Good.
I managed to keep my nose clean. Top speed, 182 kilometers an hour. Yeah. It doesn't sound that much, but then when you're 40 centimeters off the ground, your eyes, it feels pretty quick.
I bet it does.
Yeah.
We've been talking to Calyx project engineer Simon Thomsen. Thank you so much, Simon.
Excellent. Thanks, James.